Okay, so this is a brief overview of the properties of energy eigenfunctions. Okay, so number one, the notation that we use if we're going to talk about an energy eigenfunction is we use the lowercase Greek letter psi, and there's a subscript which denotes which energy eigenfunction we're talking about. And so far, our energy eigenfunctions have only depended on one spatial variable, which we call x. Okay, so psi sub n of x with lowercase I indicates we are talking about an energy eigenfunction. N will typically be some integer. If we're talking about the particle in a box, the integer could be 1, 2, 3, and so on. Okay, n equals 1 being the lowest possible energy eigenstate for the particle in the box. That will also have the lowest energy. So we'll call that the ground state. The system we talked about yesterday, the harmonic oscillator, in fact, can have n equals 0. N equals 0 is smaller than n equals 1, so the ground state for the harmonic oscillator will have n equals 0. The ground state for the particle in the box, n equals 1. So it will depend on the system. But we'll always denote the energy eigenfunctions with a lowercase Greek letter psi. There's going to be a subscript which indicates which particular energy eigenfunction we're talking about. Okay. So what's the property of the energy eigenfunctions? Well, they describe states that your quantum mechanical system can be in which that system has a precise energy. Okay. So for the particle in a box, right, the system is an electron, and it's confined to be in some limited region of space. It turns out there are certain states that electron can be in which the energy has a precise value. Okay, and so those states are known as the energy eigenstates or the energy eigenfunctions. Okay, and so if the state variable for my system, which I call big psi, capital Greek letter psi, this denotes the wave function. And now the wave function can actually be much more general than just an energy eigenfunction. So this is a really special case to say that the wave function for my electron is equal to the first energy eigenfunction. But if that is the case, if my wave function is actually equal to the first energy eigenfunction, then I know the following thing is true. I know that my electron has a precise value of energy. And because it's in the first energy eigenstate, right, little psi sub 1 is what the wave function is equal to, then I actually also know what its energy is. The energy value is whatever E sub 1 is. And we can actually compute what E sub 1 is. That's a formula that we can evaluate. But that's not the focus right now. The focus right now is on this property that if you are in if you can say that you are in an energy eigenstate, which is the same thing as saying my wave function is equal to an energy eigenfunction, then you precisely know the energy of your system. And that's a very special state to be in. Okay, a couple of more things mathematically that are important about the energy eigenfunctions. And this is what we're going to apply to compute the expectation values. So number one, the energy eigenfunctions satisfy this equation, which is known as the time-independent Schrodinger equation. So on the left-hand side of that equation, I have h hat, which is an operator related to energy. It's the energy operator. H hat acting upon my energy eigenfunction is exactly equal to some energy value, some energy eigenvalue multiplied by the same energy eigenfunction. Okay. So if I were talking about the first energy eigenfunction, like I was in this line here, h hat upon psi sub 1 of x would be equal to E sub 1 times psi sub 1 of x. E sub 1 would be the actual ground state energy value. It would just be a number. So this is also a really special relationship because h hat is an operator It has derivatives in it. It modifies this function. It modifies functions in general. And the energy eigenfunction is a special function in that when you apply the energy operator to it, you get exactly the same function out, just multiplied by a number. Okay, so that's one really important property of the energy eigenfunctions. And the other really important property is that if I take products of my energy eigenfunctions with their complex conjugates, so here I've got some energy eigenfunction psi sub n, complex conjugate, multiplied by the same energy eigenfunction psi sub n, and I integrate the product of that function over all space, I get the number 1. Okay, so this thing right here, right, the product of these two functions is itself another function. So we can imagine this is some curve, and if I take the total area under that curve, it turns out to be 1. Okay. So this is one property of energy eigenfunctions, and I can say this statement about any of them as long as I'm taking the product of energy eigenfunctions and their complex conjugates with the exact same state number n, right? So I could say psi sub 1 star, psi sub 1 of x dx integrated is equal to 1, psi sub 10 star of x, psi sub 10 of x dx integrated is equal to 1. But on the other hand, if I take any two different energy eigenfunctions, so in this integral right here, I have changed from psi, I'll move this so hopefully it's more visible. I'm going to write this bigger. I'm just going to change this integral here, so I can't see the margin. So now I'm going to write the integral still over all space, but I'm going to feed the integral two different energy eigenfunctions. One I'm going to call psi sub m star of x, right? And the other one I'm going to call psi sub n of x dx. And I'm going to say that the number m is not the same as the number n. So this could be 1 and 3, 1 and 2, 5 and 6, doesn't matter. Any pair of energy eigenfunctions which are not the same integrated over all space will give you 0. Okay. So those are the mathematical rules that the energy eigenfunctions obey. And so knowing those rules and applying them is the key to being able to compute the expectation value of energy, which will be the subject of the next video.